So our topic for today is this from structure to property. So we wanted to show you the whole workflow, and we would like to start with a COSMO file creation first. Then I will talk a little bit about conformers and conformer treatment. Then about COSMO files and database, that we can store them and reuse our files. And at the end, we will do our property prediction with our self-made COSMO files. So first of all, what is our goal? We would like to predict a thermodynamic property, like here in this small picture, it's some VLE, so vapor liquid equilibrium, that we are interested in. And what do we need to predict this equilibrium? So as we have heard this morning, we need COSMO files. So, and then we can use these COSMO files to do COSMO-RS, our statistical thermodynamics approach, and we will do that with the program COSMO-Therm that we have already seen this morning. So where do we get COSMO files? As Frank explained, COSMO, it's a quantum chemistry approach, and it's included into a couple of different quantum chemistry codes, such as turbomole and demole. And what we need for these calculations are the structures. So we have 3D structures of the molecule, including hydrogens. So for the quantum chemistry, it's just the position in space is important. So bond types are not important at all. And we can use these structures to do our COSMO calculations. But of course, the COSMO-RS calculations can reuse the files. So if you once have a file set for, let's say, ethanol, you can use it for all calculations where you like to use ethanol in. And therefore, we can also store our COSMO files in a database, or you can also do it so every customer can do it. And then you can make your own database for your projects and use your files and reuse them. So you just have to do the quantum chemistry once for each compound. So how do we do it? We will do a quick turbomole calculation on our own now. This is the turbomole program, the quantum chemistry program. You can do a lot of quantum chemistry with turbomole, from density functional theory, Hartree-Fock up to post-Hartree-Fock methods. But we will do a very simple thing now. We will do a calculation for methanol. So first we have to define our geometry. That's why our geometry button here is red. And we will try to do it with the SMILES. So we will use CO, which is the SMILES for methanol. And let's say SMILES to 3D. And then I get my methanol here. So here I have the 3D representation of my methanol. And I close, and now it's green. So here you can see the Cartesian coordinates of my methanol. Now I can do some quantum chemical settings, like the so-called the atomic attributes, basis sets, and all these things. But we also have a shortcut. So for our COSMO-RS calculations, we have all the quantum chemical types that we need here defined as templates. So we can use a kind of default COSMO-Therm job template, and here we'll use this COSMO BPT ZVP. That's the name. And what it does is it makes a geometry optimization. So for the expert of the BP functional and the TZVP basis set. So it will do a geometry optimization, optimize the structure of the molecule in the perfect conductor. That's what we would like to do. I say apply my template. And now you can here see the settings. This is the basis set, as I said, is TZVP. We will see that the level of theory is density functional theory, DFT, and I will make a geometry optimization that's type geo here. And all we have to do now is that we will start it locally here on my local computer. We'll save the input files, and then it's running here. So now we have to wait a few seconds. It's a small molecule, but it still takes a few seconds. That's why we cannot do bigger molecules here in this demo. And now we are ready, and we can here see the cycles down here. This is the optimization of the structure until the structure doesn't change anymore, and we are ready. So what we have now, we have info about the energy, for example, here in this window. And we could also have a look at the structure here. But it's not changing a lot because it's a simple molecule. But we are interested in the COSMO file, and we can have a look at the COSMO file here. These are the pictures you've seen on the slides today. This is the sigma surface of the COSMO file, so the response of the perfect conductor. This is what we can see here. So now we have our first COSMO file for methanol. This is one approach. Okay. As Johannes already mentioned, there's also a kind of fragmentation technology. So if you think about a big molecule, which is too large for quantum chemistry calculation, or just if you want to have a very fast method, you can use the COSMO-FRAC technology, which is implemented as well in COSMO-QUIC, the program Johannes already showed. And the idea is to compose a large molecule from fragments of pre-calculated molecules. So we will see here in this gray box, we will see a molecule that we like to calculate. We don't have this molecule in our database. We will search for the fragments of this data of this molecule. So we make a fragmentation, that's where the name frag comes from. And we take this part here of this molecule, the molecular surface, and the other part of the molecule on the right-hand side. And then we combine them because the sigma profiles are somehow additive. This is of course not exact, but it's a very quick approach. And that's where the name COSMO-QUIC comes from. And then you can do a lot of calculations, and all you need is a big database to search your fragments. So the fragments will be searched with the so-called Unicode. That's a kind of fingerprint approach, so that you can figure out the fingerprint or the Unicode of a special atom in a molecule, and then you can search in the database a good representative for your sigma surface for your atom. Okay. What we have done until now was just doing the calculation for one molecule, one structure, but we all know that that this is not always that simple, because we have to take into account conformers. So conformers are different molecules which have the same connectivity but different structure. And of course, they are different and they will influence our calculations. So the population of the different conformers depend on the temperature and the environment, right? We have a gas and solvent and a mixture of solvents. All this changes the population of the different conformations. The problem is that some people talk about a conformational explosion. That means if you look at our small molecule here at the right-hand side, we have two torsional angles we could change. We could turn them around. And of course, you have a couple of possibilities with the first angle and a couple of possibilities with the second angle. And if you combine them, then you get something like this tree here. And you can easily see that's an exponential problem. And so we will come up at the end with a lot of different conformers, and that's what some people call conformer explosion. And it would be really hard to check all the conformers. So why should we bother? As I already said, they have different energies and structures, and the results of the calculation depends on the conformer ensemble. And how can we deal with it? It is the theory is straightforwardly implemented in COSMO-RS, which I will show you on one of the next slides. And we have to choose a suitable conformer set. We cannot check the full conformational space, but we somehow have to find a suitable set. So, and how can we do that? Unfortunately, there is no simple answer, but there are useful procedures. So how do we deal with the conformers in COSMO-RS? We have a self-consistent treatment in COSMO-RS. You have seen the equations this morning from Frank. And we consider a compound as an ensemble of conformations. So we have a COSMO file for each conformation. But these are not different compounds. These will represent one compound. And so the population of of the conformers in the ensemble will be calculated by the Boltzmann statistics. So that's the formula we can see here. This pi here is the fraction or the population of the conformer J in the solute S of my whole ensemble of conformers. So, and you can see here that the free Gibbs energy is here in this formula. That's the COSMO energy plus the chemical potential. And now we have the problem that to calculate my conformer population, I need the chemical potential. But I get the chemical potential if I solve the COSMO-RS equation, and therefore I need this pi here, this conformer fraction. So therefore we have a second iteration loop here. We first solve the COSMO-RS equation, then we calculate the chemical potential of the conformers. And with this chemical potential, we can calculate this equation here. And I have the fraction of the conformers now, a better one. And I go again into this loop and solve the COSMO-RS equation again. So, and if you realize if you do calculations with a lot of conformers that the calculation slows down. And this is due to the second loop. Normally, we don't have, with this iteration, we don't have convergence problems. It's quite rare. Okay, one example. Here we have aspirin in water and in hexane. So our aspirin here has 3 different conformers. We call them C0, C1, C2. This is our nomenclature for conformers. And the 0, 1, and 2 refers to the COSMO energy. So that's the energy in the COSMO file without any mixture and without any chemical potential. So aspirin 0 has the lowest quantum chemical energy. And we can also see here the different structures at the bottom. So we can see here the acid group does not have a hydrogen bond in the first one, and it's somehow similar in the second one, but in the third one, the C2, we see a hydrogen bond here. Okay, if we look at the chemical potentials or in that the conformer population in water, this is here the blue values, water at 25 degrees, we can see that the first 2 are nearly equally populated, and the last one is nearly neglectable. If we go to hexane, which is apolar, we will see that the third one plays a role. So why is this? If we can see here the hydrogens, which are the polar hydrogens of the acid group, and they have a peak here. This is the hydrogen bond donor peak. And of course, in water, hydrogen bond donors are important and can play an important role and make interactions. Therefore, they are important in water. And the third one, this is the red curve here, does not have this peak because here the hydrogen bond is blocked. And so it does not play an important role in water, but in hexane, the hydrogen bonds are not that important, and it plays an important role in hexane. Here is another type of calculation. This is the octanol water partition coefficient that we have calculated this morning. And again, we can do this using conformations. So here's the number of conformers in the set, and I can use all conformers. That's the first column. And the second one is just using the C0 conformer, so the lowest energy COSMO conformer. And you can see if you have a look at the full RMSE, that in general, it works better if you use a full conformer set. Nevertheless, sometimes you have some kind of error cancellation or other effects, and you can see that here, for example, that 1,2-diaminoethane, it works pretty well if you just use the lowest one, right? Even better, even a little bit better than with the full conformation set. But in general, the root mean square error should be smaller if you use a proper conformer set, especially if you have systems with polar interactions and hydrogen bonding. Okay, now we have to think about how can we search conformers. And in order to find this suitable conformer set, what do we have to find? And it's essential and sometimes pretty hard, at least to get the global minimum. So the C0 should be the global minimum because this is normally the most important conformer. And a perfect set would be a set which is well balanced, and that means a set that contains all conformers that have a significant effect on the results of all kinds of solvents and mixtures we would like to calculate. Of course, this is hard to do because it's a wide variety of possibilities. So we can do brute force calculations. So theoretically, one could calculate the complete set of conformers on some level of theory. But for quantum theory, this is it takes too much time, it's too costly, and therefore you can only do it for very small molecule due to the conformational explosion. And you can use all kinds of other intelligent approaches, and there are a lot out there. But always the quality of the conformation set depends on the procedure that you're using. So you have to find a good compromise between the costs and the quality. Okay, our COSMO-Conf toolbox, that's a conformation generator in a way as designed as a toolbox that has procedures that can be defined by a secret of unit operations. So we have here on the left-hand side, we have an input set of conformer structures. We will do some kind of calculation with it and an output set. And we can combine a couple of these calculations, so starting with an input set, first calculation, second calculation, and so on, up to an output set, or also optionally write our output set for each step as well. And this can be used in a graphical user interface and in a command line. And we have also predefined procedures that can be used if you like to do a COSMO-RS calculation afterwards. So to ensure that you have the right level for the COSMO-RS calculation. So what are our tools which are in the toolbox? Our unit operations. We have a couple of quantum chemical calculations, the ones you have seen before from Turbomole, the DFT calculations, but also some semi-empirical methods which are faster with the so-called MOPAC program, AM1 and PM3. We have conformer generators, so we have a conformer generator from RDKit. We have a conformer generator balloon, and in our standard procedure we combine these two. And we also have a homebrew conformer generator that is mainly using or changing torsions that change the polarity of the hydrogen and hydrogen bonding. So that's made with COSMO-FRAC and with the MOPAC program. So then it's, of course, you need also some other tools like data sorting and reduction and adding and writing, and quite important, clustering. So you have to narrow down the numbers of conformers. This is what we are doing then in the clustering. So we have different types of clustering. The first one is GeoDis and GeoCheck are two methods which use the local structural similarity. So we will not calculate an RMS of the whole molecule, because if you have a big molecule and this just a very small change in an unpolar group, then you get a bigger change in the RMS, so in the structural difference between the molecules, and therefore we just look at local molecules, and at the end we check for the biggest local similarities or local differences we could find between the two molecules. This is our GeoCheck. Another one that one can use is clustering using the sigma match similarity. We have seen the sigma profiles, so we can check how equal are the sigma profiles of the molecules. Then, of course, you can simply use the nuclear repulsion energy. It's a very brute and rough measure. And we can also use the chemical potential, and this is what we are doing at the moment. So the conf select, the second one here, is using the free Gibbs energy in solution. So we have defined a couple of different solutions, or simply files and mixtures. And then we are checking what happens if we take one conformer out of our ensemble. Can we do it without losing too much accuracy? And so with this procedure nowadays, we are narrowing down our conformer set with the idea to keep the quality of the set we started with. Okay, now I will show you a little bit COSMO-Conf and how it works. Let's go to the program. So this is the surface of COSMO-Conf now. First, we will make a new job. We can call it test. Oh no, better ethanol, because this is what we want to do. First, what we have to do, we have to define our start conformers. So ethanol is not the most important molecule with a lot of conformers, but because the calculation takes some time here for the presentation, it's a good molecule to show you how it works. So now we have methanol, that's not correct. And I edit the selected one. There is one, so now substitute with small common CH3 attach, and now we have our ethanol. We save that and go back. So here's our start structure ethanol. And now I have to define my job definition, my toolbox, the tools I want to apply. Of course, I could do something simple and add step by step. For example, starting with the quantum chemistry, doing a PM3 gas phase calculation and all this. But as I have told you, we have predefined procedures. So I can go here, choose template. Now we are there. So here we would like to use the fine level. As Frank mentioned, this is our standard, and we will create Cosmo and gas phase files at the same time. So this is the procedure now. I can start it. I can check here the number of CPUs. For my system 4 should be enough. And I run it locally. Now we can see that the job is running here on the left-hand side in the job list. And we can see what happens here. First is our balloon conformer generator is generating 107 conformers. Then our RDKit is starting and is creating 200 conformers. We add them, we have 307. Then we go to the reduction, to the Unicode reduction. This is just checking with the Unicode if it's still the same structure. And I have 307. Then I sort it by energy. This is trivial. And then I make this cluster geocheck, structure clustering, and I can narrow it down to only 2 molecules. Then I'm starting to do my first DFT COSMO calculation, the one we have seen before in TurboMol, and there will be a BPT-ZVP COSMO calculation. I have 2 molecules, and now I will go on with 2 molecules, doing one step after the other. So the important step is for us here conv select now, because here I will use the chemical potential, or better, or 3 Gibbs energy in the mixture to reduce my conformer set, but because I have only just 2 conformers, there's not much happening here. So this is now getting a little bit more complicated because, as I said, the fine level is a procedure that consists of 2 steps. We first will create the TZVP molecules, and then we put the fine level on top of it. There's a so-called single point. That's why we will see here different output sets. So TZVP COSMO, TZVP gas, and the fine level gas and fine level COSMO. So here we have the 2 conformers. Let's have a look. So, and the only difference that we can find is the torsion of the OH moiety here. Both are staggered, but you have the 2 possibilities that you can have here if this group is staggered. So these conformers are extremely similar. As we can also see here in the relative energy, this is pretty much the same energy, right? So what can we do now with our molecules? We will save the sets. So I will go here and say, okay, extract my results. I have some NordicPOP directory here, and I will save them. And if we now go to the NordicPOP directory, then we can see 2 sets. That was the TZVP with 2 conformers, COSMO and energy file. So the COSMO file is the COSMO file we have seen before, and the energy file holds the gas phase energy. And we have the same for the TZVP level here. Okay. Now we have our confirmations, and we are nearly ready to start. But we have seen that we can save everything in a kind of database. So what is the database? The database is simply a collection of COSMO files. And Frank showed you a couple of slides concerning the accuracy of COSMO-RS and the parameterization, and we have different parameterizations. And because the parameterizations depends on the COSMO file on the quantum chemical level, we need to create the right file on the right quantum chemical level, and we have a database for each parameterization. So the first is the fine level, the TZVP, then it's a cheap one, a very fast one, SVP AM1, and we also have one for the DMOL program from Material Studios. So what is inside a COSMO file? So we have seen some nice pictures, but here, this is the real world. So we have surface segments, surface patches, and each of the patch has the surface charge, the so-called sigma, charge per area. And this is what you can find in a file. There's simply a list of all segments with the charges on it, and also the full energy of the molecule, which is also needed. So we can create a COSMO base. And how does it look like in COSMO Therm? As I said, you can choose the parameterization because the database must fit to the parameterization. Then you can load your compounds that we have seen this morning in our demo as well, and we can add databases. So before we add database, we have to make a databases, and this is what we would like to do now. I open the database editor, and I make a new database. NordicPOP, and this will be MyDB. Okay, so we have a multi-level database, all levels, and we don't need info, that's it. So now we can add the files from the directory we have seen before, which are here, the fine level files. Okay, and also the other level, the TZVP level that we have calculated. Also 2 files in there, the files we have seen before, and now we could use this database. Okay. So we have a database now. Now we have all the steps that we need to do our statistical thermodynamics, our COSMO-therm calculation. This is what we would like to do now directly in the COSMO-therm program again, so we don't have so much slides, more programs. And first, what we need to do, we have to add our database because we would like to use our own ethanol and not the one of the database. So we have done all the work. We would like to use it now. And we add the database here in NordicPOP. That's MyDB. Oh, come on. There's the DB file. My mouse has some problem. I select it. And yeah, database level MyDB is okay. And now we can see that we have the MyDB database in here. Saving. So here you can find again the different levels. So we are now in the TZVP fine level, and here you can see the TZVP fine parameterization. And so now we can go to the database, and we can see different databases. We have the big COSMO base 21. We have the one which is shipped with the program, and we have our small My database. So if we do this, then we can just see our ethanol because it's the only compound we have loaded, right? So I use the ethanol from this database, and I use some other molecules from the other databases because just ethanol is not that interesting. So some water, maybe hexane. Now I have my compounds. I go to the properties section, and now we will do the simplest property that we can calculate, the so-called mixture. And we will do a mixture with pure water at 25 degrees, add the job, and then run the calculation. So we are calculating now the chemical potential of our ethanol in water at infinite dilution at 25 degrees. And here we have the results. So this is the chemical potential of our ethanol. So we talked about conformers, and we can also see some conformer properties. So let's go to this tab. And here we can see the different conformers of ethanol. We have used two different conformers. That's correct. Here you can see that's the full E COSMO plus the E plus mu is the full Gibbs free energy in this mixture at this temperature. And here we can see that's the fraction or the population of the conformer in the liquid. So we have 46% of ethanol 0 and 53% of ethanol 1. So if we do another job, we clear it, and we do another job like pure hexene, what happens then? And we go again to our conformer properties, and now we see that it's pretty much the same. It has turned around a little bit, but there is not much difference because, as we have seen, our ethanols are pretty similar. There is a small difference, and there's a difference bigger than the threshold we defined in our ConfSelect procedure, but they are pretty much the same. So we started with a VLE, vapor-liquid equilibrium. That was the first picture I've shown you when I told you we would like to calculate some properties. So we will go to the VLE panel at 25 degrees, a binary, so just using ethanol and water. Clear this, add our binary, then we do the calculation. And then we can do some plots. For example, the X1, that's the mole fraction in the liquid phase, and the Y1, that's the mole fraction in the gas phase, and we get this typical plot here for our VLE. So now I close the circle, and we have calculated our property. And of course, you can also calculate a lot of other properties, like we have seen in the morning, log P, log D, pKa, solubility. We have read about co-crystals. We have now seen chemical potential. Activity coefficients are quite similar. Phase diagrams, also interesting for reaction, would be delta G of solvation. And we can also do a couple of QSPR yeah, we have a couple of QSPR models, or you can also use COSMO and COSMO-RS to create QSPR models. Okay, I hope I could show you a little bit or give you an impression about how we do it, how we go from molecules to properties. And I'm a little bit too early, but I would like to stop now because we have a couple of questions for our Q&A session. And that gives us a little bit more time for discussion. So thank you for joining this session and see you in the Q&A.